Hey folks, in lesson 14, we're going to develop the concept of a generalized angular momentum and then also introduce this angular impulse, which is similar to linear impulse, and use that in a couple of example problems. So recall from lesson 13, we introduced angular momentum, and specifically we introduced an angular momentum form of Newton's second law that we could use to derive the equations of motion for a system. But there was a restriction involved in that, and that restriction was that we could only calculate angular momentum, or we also called it moment of momentum, about a fixed point, or an inertially fixed point. And so we're going to develop this generalized angular momentum in which we can now use that about any point, whether it's inertially fixed or whether it's accelerating. So let's say that we want to develop, or that we want to calculate the angular momentum about point Q. Then let's go ahead and define some of the kinematics here, because we can always define the position of point Q and the velocity of point Q relative to an inertially fixed point. So here we've got our position vectors. So this is r of Q with respect to O, where O is an inertially fixed point. And then position vector of r of P with respect to O. Then we know that the position of r P with respect to O is equal to r Q with respect to O plus r P with respect to Q. And so we can differentiate that with respect to time and get the velocity of P with respect to O. So this is our inertial velocity of our mass P is equal to the velocity of Q with respect to O, observed in the inertial reference frame, plus the relative velocity of P with respect to Q, as observed in the inertial reference frame. And so, if we calculate the angular momentum of the mass P about point Q, then our angular momentum, P with respect to Q, as observed in the inertial reference frame, is equal to the position vector, P with respect to Q, crossed with the mass multiplied times the inertial velocity of P with respect to Q. So it's multiplied by a relative inertial velocity. And so to write that out completely, we would get, and write this out with respect to an inertial point, then we're going to get r of P with respect to O minus r of Q with respect to O crossed with the mass multiplied times the velocity of P with respect to O minus the velocity of P with respect to Q, or Q with respect to O. And so this gives us a generalized expression, and it's a generalized form of angular momentum that you can use when calculating the angular momentum about any point. Now notice that if the point that you're calculating this about, because we're using Q, if the point is inertially fixed, then we end up losing these two other terms. So the velocity of Q, or the position vector of Q with respect to O, ends up, if it's an inertially fixed point, being 0, and the velocity of Q with respect to O ends up being 0 as well. And then we're back to our normal expression, or the expression that we developed in lesson 13, which was the moment of momentum, the angular momentum about a fixed point, an inertially fixed point. So hopefully you've noticed that the usefulness of these expressions is that we can use them to develop our equations of motion, which means we need to have these expressions, these angular momentum, in particular this generalized angular momentum, using Newton's second law. And we've done this before by taking the time derivative of the momentum, the linear momentum or the angular momentum, and that's what we're going to do here. So if we insert this expression into our time differentiation, as you see here, then let's just take the time differentiation and see what we get. So d dt as observed in the inertial reference frame, of our angular momentum with respect to point Q, as observed in the inertial reference frame. And let's just apply the chain rule here. So we get the time differentiation in the inertial reference frame of r of p with respect to q cross with mp multiplied times our velocity of p with respect to q as observed in the inertial reference frame. And then this will be plus r of p with respect to q crossed with, we can pull our mass out, our time differentiation of the velocity of p with respect to q as observed in the inertial reference frame. So we've simply applied the chain rule to each of the expressions here, which give our relative, which gives our angular momentum relative to a point, just any general point. And so we'll see here that we're going to get the velocity of p with respect to q as observed in the inertial reference frame crossed with mp v velocity of p with respect to q. And so the cross product of anything with itself is 0. And so the only term that we have left now is our position vector r of p with respect to q crossed with the mass multiplied times the time differentiation of the velocity of p with respect to q. So the time differentiation of v, or the time differentiation of our velocity of p with respect to q, is the acceleration of p with respect to q. So it's a relative acceleration. And so that means our only term that we have left now is this r p with respect to q cross with our mass times this relative acceleration. Complete the expression. So let's take a closer look at this expression. R of p with respect to q, our position vector, cross with the relative acceleration. And the relative acceleration, write this out, the relative acceleration is nothing more than the difference in acceleration between the acceleration of point P relative to the inertially fixed point minus the acceleration of point Q relative to the inertially fixed point. And you can see that from our differentiation here. If we differentiate our velocity, we would get acceleration of point P is equal to the acceleration of point Q relative to the inertially fixed point plus the acceleration of point P relative to Q. And so if we come back down to our expression and then we separate these two parts, then we get r of p with respect to q crossed with the mass multiplied times the acceleration of p with respect to o in the inertially fixed reference frame minus r of p with respect to q cross with the mass multiplied times the acceleration of q with respect to o in the inertially fixed reference frame. And here you should see something that you recognize, which is the mass of point P multiplied times the acceleration of point P with respect to a point that's fixed in the inertial reference frame. That's nothing more than the sum of the forces that are applied to that point using Newton's second law. So there's where Newton's second law fits in, and so then our final expression here contains this r cross f, and so this is now the moment of P with respect to Q, not P with respect to O as we did before, but P with respect to Q, because it's the moment of the force about the point Q being any arbitrary point. So our final expression of Newton's second law in this generalized angular momentum form is the time differentiation as observed in the inertial reference frame of the angular momentum as observed in the inertial reference frame about point Q is equal to the moment of P about point Q minus R P with respect to Q, that relative position vector, crossed with the mass times the acceleration of point Q as observed in the inertial reference frame. This is a very powerful expression because it's giving us the inertial rate of change of the angular momentum relative to any arbitrary point Q. Point Q doesn't have to be fixed within an inertial reference frame. It can be accelerating. It can be moving however it wants to move, and we can still calculate this expression. So notice here that this left-hand side looks just like what we did with in lesson 13, where the time differentiation is equal to a moment. But we've got this extra term, and this extra term looks just like a moment as well. And so it even has a name. It's a corrective factor that's called an inertial moment. And all this is to say is that whenever point Q is accelerating, that you have to use this correction factor and subtract, okay, this is a minus sign, you have to subtract the inertial moment of that accelerating point. And if you use this expression, if you start with this expression in any of your problems, then you're always going to get the right answer. And so that's why this is so powerful, is because this is the expression to always use, unless you can recognize that you're about an inertially fixed point, and if that's the case, go back to the simpler form because the math is a little bit easier. Let's apply this general form to a system in which we have to apply it, in which we'll take the angular momentum about an accelerating point. And so recall, in lesson 11, we showed that the equation of motion of this system is theta double dot is equal to minus g over L sine theta. And then there's another term, minus a over L cosine theta, which accounted for the fact that the box in which the pendulum is in is actually accelerating. It's not an inertial reference frame. And we said that, if you get your fuzzy dice hanging from your mirror in your car, when you accelerate, it tips back, and it looks like it's tipping back towards you, and that's the reason. It's because of this term that's on the right-hand side. So let's apply our reference frames like we did in lesson 11. And here we see an inertial reference frame I, which has the unit vectors E1, E2, and E3. And they're defined just like what we did last time, with the origin at the inertially fixed point O. And we have the reference frame B, in which B1 is defined as along the pendulum. We have B3 defined out of the page along E3. And then we have a B2, which is orthogonal to both of those vectors. And so this has an origin at O prime, which is not an inertially fixed point. In fact, it's a point that's accelerating to the right or along E2 with an acceleration of A. And so our kinematics are R of point P with respect to O is equal to R of O prime with respect to O plus R of P with respect to O prime. And this is X in the E2 direction plus L in the B2 direction, or B1 direction. And then our velocity of P with respect to O is equal to X dot in the E2 direction plus L theta dot in the B2 direction. So let's derive the equations of motion using this generalized form of angular momentum within Newton's second law. And so our expression, just copied from the other page, is the time derivative of the angular momentum about point O prime this time. And this is going to be equal to the moment of point P, of the forces about point P, about O prime, minus this inertial term, inertial moment, P with respect to O prime, crossed with the mass of P multiplied times the acceleration of O prime with respect to O. The procedure here is just the same as what we did for linear momentum and what we did in the last lesson, in which we look at each of these terms that we have, both on the left-hand side and on the right-hand side, and let's calculate each of them. So we'll calculate for the left-hand side our angular momentum about point O prime. We'll take the time differentiation of it. We'll be done with the left side. Then we'll calculate the moment, and then we'll calculate this inertial moment, put it all together, and then we'll have our equation of motion. So for the left-hand side, the angular momentum of point P with respect to O prime, so O prime is not an inertially fixed point, R, P with respect to O prime, crossed with our mass multiplied times the inertial velocity of P with respect to O prime. And so we know that R, P with respect to O prime is equal to L in the B1 direction, and we know that our velocity of P with respect to O prime is equal to L theta dot in the B2 direction. Let's take the cross product of those. So angular momentum of P with respect to O prime is equal to L in the B1 direction, crossed with our mass multiplied times L theta dot in the B2 direction. And this simply gives us our mass L squared theta dot in the B3 direction. And let's take the time differentiation of this. d dt observed in the inertial reference frame, P with respect to O prime. Using the chain rule, we get the mass of P, L squared, theta double dot in the B3 direction. And this is, then using the chain rule, we get MP L squared theta dot multiplied times the time differentiation as observed in the inertial reference frame of B3. And the time differentiation, d dt, of B3 is going to be equal to omega B as observed in the inertial reference frame cross with B3, and omega of B reference frame B observed in the inertial reference frame is equal to theta dot in the B3 direction. If we're crossing that with B3, then this term ends up being 0. And so the time differentiation, or our entire left-hand side, is right here. Alright, so there's our left-hand side. So let's calculate the right-hand side, which means that we need to come up with an expression for the moment about point O prime, which is moving, and then our inertial moment. Let's tackle our moment first. So the moment P about O prime is equal to R cross F. So this is the position vector of P with respect to O prime, cross with all the forces on point P. Now to get all the forces on point P, we need a free body diagram. We'll do this the same way we did last time, in which we have mass times gravity, the force due to gravity in the E1 direction, and then we have a normal force, which is in the negative B1 direction. And so Fp is equal to all the forces on that particle, so it's minus n in the B1 direction, plus mg in the E1 direction. And so this gives our moment, P with respect to O prime, is equal to L in the b1 direction crossed with negative n in the b1 direction plus mg in the e1 direction. And so we also know that E1, if we convert this into the B basis, is cosine of B1 minus sine theta B2. When we plug this in, we'll carry down our L in the B1 direction crossed with, and it's negative n in the B1 direction plus mg cosine theta in the b1 direction minus mg sine theta in the b2 direction. And so our moment, because b1 crossed with b1 gives us 0, and so none of those terms matter, but b1 crossed with b2 gives us b3, so we get negative L mg sine theta in the b3 direction. Alright, that takes care of the moment on the right hand side of the equation. And so now let's get this inertial moment. The inertial moment is r of p with respect to O prime crossed with the mass of p multiplied times the acceleration of O prime with respect to an inertially fixed point as observed in the inertial reference frame. We know that r of p with respect to O prime is equal to L in the b1 direction, and then the acceleration of O prime with respect to O is simply equal to x double dot in the e2 direction, or it's given as a in the e2 direction. So once again we have a mix of coordinates, so let's change our e2 into b1, b2, and we do that by saying e2 is equal to sine theta b1 plus cosine theta b2, and let's put all that in. So our expression here, r p with respect to O prime cross with our mass times our inertial acceleration of O prime with respect to O, is equal to L in the b1 direction crossed with ma multiplied times sine theta b1 plus cosine theta b2. And so our final expression for our inertial moment is L times the mass of the particle times the acceleration cosine theta in the b3 direction. And so now we plug each of these terms into our overall expression, where we get the mass of point P, L squared theta double dot in the b3 direction is equal to negative mg sine theta in the b3 direction minus L m a cosine theta in the b3 direction. And so everything's in the b3 direction, which is good because this is planar motion. And then using this expression we solve for theta double dot, and when we do that we get theta double dot is equal to minus g over L sine theta minus a over L cosine theta, which is the same as before. So we can use this generalized form of angular momentum with Newton's second law embedded in it to calculate our equation of motion without having to go through all of our constraint forces and all of our other things that we did earlier, using Newton's second law straight up. And then just as a reminder, the other nice thing about this is that we only had to calculate our inertial velocity. We ended up taking some time differentiations, but by using angular momentum or linear momentum from a few lessons ago, we're able to sort of bypass some of the more complicated calculations for our acceleration. Alright, let's go back to a concept that we developed at the very beginning of this chapter, and that's the relationship of momentum and impulse, or momentum and the time derivative of force in the case of linear momentum, or in this case, moment in the case of angular momentum. And so, similarly to linear momentum and linear impulse, we have a relationship between the angular momentum at time 2 and time 1, and the difference between those is going to be the integral of our moment of p with respect to O across time. Now, we're only looking at this in that special case, that one special case, in which we're calling that an impulse. And the impulse, which we draw as, or which we write as, the impulse has a bar over, which is the impulsive moment from t1 to t2, where that's occurring over a short time interval. And so remember, we use this to apply initial conditions, and we also use this to instantaneously change the momentum of a system, which would be changing the velocity, either the speed or the direction or both. And so we get this expression here that relates the two together. And so this is where the moment, as we've done before, the moment of p with respect to O is going to be r of p with respect to O cross with all the forces at time p. So then this gives us a tool now to be able to vary force p in an impulsive way to create an impulsive moment, or an angular impulse. And so let's apply this to an interesting problem in which we have a tether ball wrapping around a pole. So let's take a look at this model, and as we look at this, we see that when theta is equal to 0, well, we've got our ball, our tether ball, point P, and then we've got its attachment to the pole. And notice that when theta is equal to 0, that's when it's completely unwrapped. And then as theta increases, that it's going to wrap around the pole, and we should see this length get shorter and shorter and shorter. So if you've played tetherball, you know the object of the game is to wrap the ball completely around the pole against your opponent. And so that's what we're modeling here with this particular model. Now the other thing to notice here is that this point this point O prime is not stationary. O prime is going to wrap around the pole as the ball and the tether itself travels around the pole too. You can see that because at theta is equal to 0, O prime is at the bottom of the pole. As it wraps around, it's always going to create this point at which the tangent is coming off. And so that's how the tether ball is going to work. In addition to that, notice that as the ball moves around the pole, L also shortens. So if we define big L as the length when theta is equal to 0, then we get the expression of L as it's changing is equal to big L minus the length that's being removed as it wraps around the pole, which is simply the arc length. So that's the radius r multiplied times theta. And so this is our constraint equation. This is what's taking this problem from a two-dimensional problem into a one-dimensional problem, where all of the expression can be wrapped up in this variable theta. So in this variable theta, we now have our state, which will be theta and theta dot. And so the problem that we're going to solve here is to find out what the impulse is, the angular impulse at any state that would need to be applied to completely reverse the direction of travel. So let's define our reference frames. First we have our inertial reference frame, in which we have E1, E2, and then E3. The origin is at point O, which is an inertially fixed point. And so E1 is defined as along O prime P, so this is along the tether when theta is equal to 0. And then E3 is out of the plane, and then E2 is equal to E3, cross with E1. So let's define our second reference frame, in which this is a non-inertial reference frame, B, with a vector ER pointing along O prime P, the vector E theta orthogonal to that, EZ, along the direction of E3. But then notice that its origin is at O prime, not at O. And then we calculate the standard things that we need to do to either transform between the bases of the reference frames or to make calculations with the time derivatives. And so now we're ready to tackle this one. Now remember, our objective is to reverse the velocity by applying an impulse. So let's write down our impulse momentum relationship, which says that the angular momentum at time 2 of point P about point O is equal to the angular momentum of point P about O at time 1 plus, here's our angular impulse, P about point O, time 1 to time 2. And so we want the angular momentum at time t to be exactly opposite of that of time 1. That would be what it would mean to completely reverse the velocity. So let's substitute that in and just say that this is negative angular momentum of point P about point O of time 1. The exact opposite is equal to what our initial condition is plus that impulse, which is what we're solving for. And so we can solve for the impulse in its form that it's in right now to get us going. And that's equal to negative 2 angular momentum of point P about point O as observed in the inertial reference frame at time 1. So we simply need, in order to find this, we simply need to develop an expression for this angular momentum at time 1 in terms of the state, because we want this to be for any state theta, which is theta and theta dot, and the geometry of the system. So here we simply need to calculate the angular momentum of point P about point O for any state. And so because point O is an inertially fixed point in this problem, we can use that simple form, that moment of momentum form of this angular momentum. So that's simply the position vector of P with respect to O crossed with the mass multiplied times the inertial velocity of P with respect to O. So let's calculate each of these expressions. So here we get the position vector, the position of P with respect to O, is going to be equal to this distance going from O to O prime plus the distance O prime, or the vector O prime, to P. And so O to O prime is negative R in the E theta direction, and then O prime to P is L in the ER direction. And we've already stated that we have our constraint, L is equal to big L minus R theta. So let's just substitute that in. So we have negative R in the E theta direction plus L minus R theta, theta dot. Or rather, theta. Need to erase those. Alright, so we've got our position vector. We know our mass, so now let's calculate our inertial velocity. The inertial velocity of point P with respect to O is going to be equal to the time differentiation as observed in the inertial reference frame of the entire expression, where it's negative R in the E theta direction plus L minus R theta in the ER direction. And so let's address each of those parts individually. And so the time differentiation of R is 0 because it's a constant. And so that's 0 in the E theta direction. And then using the chain rule, it's negative R multiplied times d dt in the inertial reference frame of E theta. This is plus, and then when we take the time differentiation of the coefficient here, then we get minus r theta dot multiplied times an er, and then this is plus L minus r theta multiplied times the time differentiation of the unit vector er. Let's take care of time differentiating these vectors. So we'll take the time differentiation of e theta. This is equal to omega b with respect to observed in the inertial reference frame cross with e theta. And so this is theta dot in the ez direction crossed with e theta, which gives us z cross theta is in the negative er direction, so it's negative theta dot er, and then our time differentiation of er is omega b as observed in I crossed with er, and so that's theta dot ez crossed with er. Z cross r gives us theta, e theta, so it's just theta dot in the e theta direction. And so next we plug all this in, so we get negative r multiplied times negative theta dot in the er direction minus r theta dot in the er direction. We'll see that these two terms cancel because we have same magnitude, opposite signs. And then this is plus L minus r theta multiplied times time differentiation of er is simply theta dot in the e theta direction. And so our velocity of p with respect to O as observed in the inertial reference frame is equal to L minus r theta multiplied times theta dot, and that's in the e theta direction. All right, let's stop just a moment and make sure that that makes sense to us. So if we go back to our diagram, we see that the length that goes from O prime to P, the length of the tether, is always going to be big L minus r theta. And we also know that the velocity is always tangent to the path. And O prime is rotating around the pole as we go. So what's interesting here is that the velocity of this path, because O prime is moving, is always going to be tangent to this path. But because it's shortening, it's always tangent to the path, but it's always going to be perpendicular to O prime to P. But because this is shortening, as we move around, we still get our spiral. The spiral is changing because of this L minus r theta. So that should show us that this expression for the velocity does make sense. So our next step is to plug this into our momentum equation. So it's angular momentum of P with respect to point O, inertially fixed point, is equal to, and it'll be this entire expression for our position, where we have L minus r theta in the ER direction, minus r in the E theta direction, cross with mass multiplied times our inertial velocity, which is L minus r theta multiplied times theta dot in the E theta direction. And so we make this calculation with our cross product. We see that an E theta crossed with E theta is going to give us 0, so the only terms we're concerned with are the r cross theta. And so we get the expression, our mass multiplied times L minus r theta squared multiplied times theta dot in the EZ direction. And so this is our angular momentum, and so we want this, like I said, for any state, but let's go ahead and put in our T1. So our angular momentum of point P with respect to an inertially fixed point O at time 1 is equal to this same expression, but simply putting in, or recognizing that each of our state variables, theta and theta dot, are functions of time, and we're only interested in at time 1 before the impulse occurs. And so our final step is simply to plug this into the expression that we developed earlier, which is that our angular impulse across that small time 1 to time 2, is going to be equal to -2 multiplied times our angular momentum at time 1. And so we get with this -2 mp L minus r theta at that time 1 squared multiplied times theta dot at time 1 in the EZ direction. So this would be our angular impulse that we would want to apply to completely reverse the direction of the tetherball. And so go back to what we're actually doing here. So we've got a tetherball game. The goal is to wrap it around the pole. And if you've played this before, you know that if you don't apply the correct force to the ball in the right direction, that the ball can just keep on going. It can glance off your hand, and you won't necessarily reverse the velocity. So this would tell you the exact impulse that you need to apply to simply change the direction with the same velocity. Now, I mentioned just a moment ago that this is done with a force. So our impulse here, it's an angular impulse, but always remember that it's an angular impulse that's based on the moment that you'll be applying over a very short time, and that is r of p with respect to O crossed with the force that you're going to put on the ball. Now that force ideally would be perpendicular. It would be perpendicular to the lever arm, r of p with respect to O. However, that's not always how you can apply that, or that's not always how you apply it. You can apply it out, which would tighten the string. You can apply it in, which would loosen the string, and so forth. But this should give you an idea about how you would make that calculation and apply that condition to change that state by changing the angular momentum. All right, see you in class.